Welcome everyone. Today, we turn to one of the most important developments in modern computer vision, vision transformers and multimodal models. This lecture builds directly on our earlier sessions on convolutional neural networks and advanced computer vision. Our goal is to understand how the transformer architecture, which was originally designed for language, has been adapted to images, and why this shift matters for global health and biomedical applications. By the end of today, you should understand patch embeddings, the class token, positional embeddings, self-attention applied to image patches, how vision transformers compare to convolutional networks, and how these ideas extend to segmentation, detection, and image-to-text multimodal systems. Let us begin by grounding ourselves in how vision models evolved. This slide shows the evolution of vision models in deep learning across a short but dramatic period. In year 2010, the state-of-the-art was the NEC-U-IUC system, which relied on hand-engineered features, a dense descriptor grid using HOG and LBP, coding with local coordinate and supervector methods, spatial pyramid pooling, and finally, a linear support vector machine. This was a classical pipeline, where humans designed the features and the learning happened only at the very end. In year 2012, supervision, better known as AlexNet, from Krzyzewski and colleagues, changed everything by learning features end-to-end with a deep convolutional neural network. In year 2014, we see GoogLeNet from Szegedy and colleagues, with its inception modules mixing pooling, convolution, and softmax layers, alongside VGG from Simonian and Zisserman, a very regular stack of 3x3 convolutions with max pooling, going from conv 64 up through conv 512 blocks, and then fully connected layers. In year 2015, MSRA introduced very deep residual networks, or ResNets, from he and colleagues, which used skip connections to train networks with dozens or even hundreds of layers. The key message is that each of these milestones drove down error on the ImageNet large-scale visual recognition challenge, and each represented a deeper, more end-to-end learned architecture. This progression sets the stage for transformers, which represent the next conceptual leap. This slide shows pre-trained convolutional models plotted as ImageNet top 1 accuracy against the number of parameters in millions, from Tan and colleagues in 2020. The red curve traces the EfficientNet family, from B0 in the lower left up through B7 in the upper right, reaching above 84% top 1 accuracy. The comparison is striking. EfficientNet B1 reaches about 79.1% with only 7.8 million parameters, matching ResNet 152, which needed 60 million parameters for 77.8%. Similarly, EfficientNet B7 reaches 84.3% accuracy with 66 million parameters, matching GPipe, which required 556 million. The lesson here is efficiency. Better architecture and compound scaling let you achieve the same or higher accuracy with far fewer parameters, which matters enormously when you want to deploy models on limited hardware in resource-constrained settings. Now let us look at the core computer vision tasks that these models perform. This slide illustrates image classification and regression together. An input image passes through convolution and pooling layers to produce a final convolutional feature map. From that shared feature map, the network branches into two heads. The classification head is a set of fully connected layers that outputs class scores. The regression head is another set of fully connected layers that outputs continuous values, in this case box coordinates. The key idea is that a single backbone can support multiple tasks simultaneously through different output heads, an idea that carries directly into detection and multitask learning. This slide extends the same idea to image classification and localization. On the left, the image passes through the convolutional backbone to a 4096-dimensional vector. One fully connected branch maps 4096 to 1000 class scores, producing predictions like cat 0.9, dog 0.05, car 0.01, and so on, which are compared to the correct label using a softmax loss. A second fully connected branch maps 4096 to 4 box coordinates, x, y, w, and h, and localization is treated as a regression problem compared to the correct box using an L2 loss. The two losses are combined into a single multitask loss, shown in red, which is what the network minimizes. On the right, you can see the loss definitions, L1 as the sum of absolute errors, L2 as the sum of squared errors, and their averaged forms, mean absolute error and mean squared error. The takeaway is that classification and localization can be jointly optimized by summing a classification loss and a regression loss. This slide introduces YOLO, which stands for You Only Look Once. The idea is elegant. An image is passed once through a CNN to produce feature maps, which are divided into an n by n grid. Two fully connected heads then operate on that grid. One produces class probabilities via softmax, generating a class probability map, and the other regresses bounding boxes. Because the whole image is processed in a single forward pass over an S by S grid, YOLO is computationally fast, which, as the slide notes, makes it useful for many relevant tasks in medicine. Speed matters when you need real-time or high-throughput detection. This slide shows YOLO applied to medical images. On the left, a brain MRI has two detected regions labeled tumor with 100% and 98% confidence, with overlaid segmentation masks. On the right, wrist and forearm, X-rays show detections labeled messed up angle at 0.86, confidence and fracture at 0.72 confidence, illustrating automated fracture and deformity detection. This demonstrates that the same object detection machinery used for everyday photos can localize tumors, fractures, and abnormal angles in radiology, giving clinicians fast, structured attention cues. This slide covers another common task, semantic segmentation. Here the goal is to assign a class label to every pixel so the output has the same spatial dimensions as the input. The architecture shown is an autoencoder, or encoder-decoder. The input is 3 by H by W. The encoder progressively downsamples through high resolution, medium resolution, and low resolution stages, denoted D 1 by H over 2 by W over 2, then D 2 by H over 4 by W over 4, and a low resolution bottleneck. The decoder then upsamples symmetrically back to high resolution, producing dense predictions at H by W. The result, shown on the right, is a segmentation map, where each pixel of the cow, sky, and grass is colored by its predicted class. This encoder-decoder pattern is the foundation for the biomedical segmentation networks we will see later. Now we arrive at the central topic, vision transformers. This slide introduces the vision transformer, or ViT, by first showing the transformer encoder block on the right, from AlexNet in 2021. The animation shows how the image is tokenized into patches, which are then processed to create a linear projection of flattened versions of these patches. This creates learnable embeddings, which are mapped spatially with positional embeddings to feed into the transformer encoder. This encoder block, repeated L times, takes embedded patches, applies a normalization layer, then multi-head attention, then adds a residual connection. It then applies another normalization, an MLP, and another residual addition. This is exactly the transformer encoder we studied for language, but now the tokens will be image patches rather than words. The dashed line indicates that this block is stacked L times to form a deep encoder. This next slide shows the full vision transformer pipeline, from LI in 2024. Here's the key innovation, and it is worth walking through carefully. An input image, here a set of brain MRI slices, is divided into fixed size patches, for example 16 by 16 pixel patches. Each patch is flattened into a vector and passed through a linear projection of flattened patches, turning each patch into a token embedding. These patch tokens are numbered 1 through 9 in the diagram. An extra learnable token, marked 0 with an asterisk and labeled the class embedding, is prepended to the sequence. Its final representation will be used for classification. A patch plus position embedding is added to every token so the model knows where each patch came from in the original image, because attention by itself is permutation invariant. This full sequence is fed into the transformer encoder, and the output corresponding to the class token is passed to an MLP head, which produces the class prediction, here choosing among brain, skull, tumor, and so on. So the profound idea is this: an image is worth n by n words. We treat patches as tokens and let self-attention model relationships between them, exactly as it models relationships between words in a sentence. Now, attention is the key to the transformer architecture, which we can contrast in 4 different ways. In a convolution, shown top left, each output attends only to a small local neighborhood of inputs, sharing weights across positions. In a fully connected layer, bottom left, each output connects to every input, but with fixed learned weights. In global attention, top right, each output can attend to every input, but the connection strengths, shown as colored arrows, are computed dynamically from the data. In local attention, bottom right, attention is restricted to a nearby window, a compromise that reduces computation. The essential difference is that attention weights are input dependent and learned on the fly, unlike the fixed weights of convolution or dense layers, which is what gives transformers their flexibility. This is the essence of how a vision transformer converts a picture into a sequence the transformer can reason about. This slide, again on attention, shows self-attention from 2 complementary viewpoints, from AlexNet in 2020. On the left is a self-attention probability score matrix for the 4-word phrase. Hello, I love you. Rows are the token doing the attending. Columns are the tokens being attended to. Each row is produced by a softmax, so its entries form a probability distribution that sums to 1. For example, the row for hello places 0.8 weight on itself and small weights elsewhere, while the row for love places 0.65 on itself but also 0.2 on I, reflecting that the subject informs the meaning of the verb. On the right, the same matrix is drawn as an undirected weighted graph, where tokens are nodes and attention weights are edge strengths, with self-loops showing self-attention. The point is that attention can be read either as a matrix of routing probabilities or as a graph of information flow between tokens. This slide overlays the attention theme on the vision transformer diagram, reminding us that this same self-attention mechanism, computed among patch tokens, is precisely the engine inside the ViT transformer encoder we just saw. The patch tokens, class token, and position embeddings all flow into that encoder, where multi-head attention lets every patch compare itself with every other patch. This slide examines what the learned position embeddings look like after training, from AlexNet in 2021. After the low-dimensional linear projection, a trainable position embedding is added to the patch representations, and it is illuminating to inspect these embeddings once training is complete. The figure shows a 7x7 grid of small heat maps, one per input patch position, where each heat map shows the cosine similarity between that patch's position embedding and every other position's embedding. The striking pattern is that each patch is most similar, shown in bright yellow, to positions in its own row and column, and similarity decays with distance. In other words, the model learns, purely from data, a notion of two-dimensional spatial structure, recovering the grid layout of the image, even though we never explicitly told it the geometry. This is strong evidence that position embeddings genuinely encode spatial relationships. Now, let's explore in some more detail what happens in the first stages of the transformer. This slide shows how queries, keys, and values are produced inside attention, from Callis in 2024. On the left, an input tensor, with dimensions number of tokens by length of tokens by batch size, is passed through 3 separate learned linear layers to produce queries, keys, and values, each with a projected length of tokens. The learned weights and biases of these 3 linear layers are what the model trains. On the right, the difference between single-headed and multi-headed attention is made explicit. In single-headed attention, the full projected length of tokens, labeled chan, is used as one block. In multi-headed attention, that same projected width is split into several heads. Here, head 1, head 2, and head 3, each of width head underscore dim, and each head performs attention independently before the results are concatenated. So multi-head attention is essentially slicing the projection into parallel subspaces so the model can attend to several kinds of relationships at once. This slide builds intuition for why dot products measure relevance from a query key value perspective. It shows 3 vectors in a 2-dimensional space pointing toward a panda, a red panda, and a fox, with angles θ1 and θ2 between them. The equation at the bottom defines similarity of 2 vectors, A and B, as their cosine similarity, the dot product of A and B divided by the product of their magnitudes. Vectors pointing in similar directions, like when comparing the panda with the red panda, or the fox and the red panda, have small relative angles and high cosine similarity, while the angle between the panda and the fox points further away from each other than the other 2 pairs and therefore are less similar. This kind of makes sense since a red panda kind of looks like an animal, in between a panda and a fox. This analogy explains why the dot product between a query and a key is a natural measure of compatibility. It measures alignment in a learned embedding space and in a transformer. The query and key projections are learned to make this alignment meaningful for the task. This slide continues the attention theme with an animated illustration. From AlexNet 2021 we have seen in previous lectures, where we were walking through how the query, key, and value projections interact to route information between tokens. Conceptually, it reinforces the same mechanism. Each token forms a query and compares it against every token's key via dot products. Those scores are scaled and passed through a softmax to form attention coefficients, and those coefficients weight the value vectors to produce each token's contextual output. Keep in mind the standard equation. Attention of Q, K, V equals softmax of Q times K transpose divided by the square root of D minus K, all times V. This slide shows a classic embedding space intuition, the king, queen, man, woman example, in a similarity embedding space. The 4 word vectors are arranged so that semantic relationships correspond to consistent directions in this nth dimensional space. The purple arrows represent a gender direction, so that moving from king to queen or from man to woman is roughly the same vector displacement. The orange arrows represent a royalty direction, so that moving from man to king or from woman to queen is another consistent displacement. The lesson is that during training, models learn embedding spaces where statistical relationships in the data become geometric relationships, which is exactly why analogy like reasoning, clustering, and semantic search emerge. The same principle applies to patch embeddings in vision. Semantically similar patches end up close together in the learned space. This slide directly compares transformers and CNNs by visualizing their learned filters. On the left are the first convolutional filters of AlexNet, showing the familiar oriented edges, color blobs, and Gabor-like textures that a CNN learns in its first layer. On the right are the first linear RGB embedding filters of a vision transformer, specifically the first 28 principal components of the patch embedding projection. Remarkably, the ViT filters also learn structured, edge-like, and frequency-like patterns, resembling plausible basis functions for representing local image structure, even though the ViT has no built-in convolutional prior. The message is that despite starting from a very different architecture, the vision transformer discovers low-level visual features that look strikingly similar to those learned by convolutional networks, suggesting these features are fundamental to representing images. This slide compares pre-trained CNNs and transformers on ImageNet. Top 1 accuracy over time. From paperswithcode.com in 2024. The horizontal axis is the year, from 2016 to 2024, and the vertical axis is top 1. Accuracy, with gray dots for individual models and a teal line tracing the state-of-the-art. The state-of-the-art trajectory climbs from Fire Cafe, a GoogLeNet variant near 68%, through ResNet 152 and SimpleNet V1, up through AmoebaNet A, FixResNext 101, and meta pseudo-labels with EfficientNet L2, and finally reaches Omnivec, a vision transformer, at above 92% by 2024. The key point is that the current best performers are transformer-based, illustrating how ViTs and their descendants now lead the accuracy frontier that convolutional networks once dominated. This slide plots pre-trained models by accuracy versus computational cost, from AlexNet and colleagues in 2021. The vertical axis is top 1 accuracy, and the horizontal axis is operations in gigaflops, with bubble size proportional to the number of parameters, ranging from about 1 million up to 150 million. You can see the full landscape here. Efficient models like MobileNet, ShuffleNet, and SqueezeNet sit in the low-cost region, while heavier families like VGG, ResNet, DenseNet, SE ResNext, and NASNet at large occupy higher accuracy and higher compute. The practical message for deployment is that model selection is a trade-off. You must balance accuracy against flops and parameter count, especially when targeting mobile or edge devices in global health settings. This slide focuses specifically on the robustness of transformers versus CNNs, from Xiao and colleagues in 2022. The horizontal axis is clean accuracy, and the vertical axis is robust accuracy, meaning accuracy under adversarial perturbation, with bubble size indicating parameter count. The plot is divided into a CNN region in blue and a hybrid region in pink, and it shows many models including ViTs, ViTb, ViTl, ViTs-AMB, D-T, Swin, T2T-ViT, ConvNext, SE ResNet 50, and MLP Mixer. The important finding is that vision transformer variants, particularly the ViT and hybrid families in the upper region, tend to achieve higher robust accuracy than pure CNNs at comparable clean accuracy. In other words, transformers are not only accurate on clean data, but also comparatively more resistant to adversarial attacks, which is a meaningful property for safety-critical medical applications. This slide shows a hybrid CNN transformer architecture for medical image segmentation, from Narella and colleagues in 2024. On the left is the transformer encoder block, layer norm, multi-head self-attention labeled MSA, a residual add, another layer norm, an MLP, and another residual add, producing the output Z-1, operating on an embedded sequence of patches. In the middle, an abdominal CT image is processed by a CNN that produces hidden features, which are linearly projected and passed through a stack of transformer layers. Here n equals 12. On the right, features at multiple scales, 1/2, 1/4, and 1/8 resolution, are progressively upsampled and concatenated in a decoder using 3x3 convolutions with ReLU, upsampling, and a final segmentation head, producing a labeled organ segmentation at 16 by H by W. This U-shaped hybrid design combines the local feature extraction of CNNs with the global context of transformers, which is a very common and effective pattern in modern biomedical segmentation. This slide compares efficient models on the accuracy versus latency trade-off, from Lai and colleagues in 2023. The vertical axis is ImageNet 1K top 1 accuracy, and the horizontal axis is latency in milliseconds, with bubble size again indicating parameters. The plot features the EfficientFormer and EfficientFormer Phi 2 families, alongside PoolFormer, Mobile ViT, Edge ViT, MobileFormer, ResNet 50, and MobileNet V2. The EfficientFormer V2 models sit in the upper left sweet spot, achieving high accuracy at low latency, showing that transformer-style models can be engineered to run fast enough for real-time and mobile deployment. The engineering lesson is that latency, not just accuracy or flops, is often the binding constraint in practice, and specialized efficient transformer designs have made ViTs viable on the edge. This slide covers useful tricks to improve computer vision models, showing two techniques side by side. On the left is data augmentation, from Dung and colleagues in 2020, showing a letter M transformed by scaling, rotation, shearing, cropping, added noise, random erasing, blur, color space changes, and feature space perturbation. The essential objective in augmentation is to apply transformations to data that help the system better interpolate across the full distribution of possible data, while preserving the original labeled class or value. This looks trivial visually, but thinking about what it represents to be able to recognize that all of these images are just M's is something remarkable visually that has taken centuries for humans to understand formally and not only intuitively. Augmentation artificially expands the training set and improves generalization by teaching the model to be invariant to these transformations. On the right is K-fold cross-validation from AppTech in 2022. The original dataset is split into training and testing sets. The training data is divided into n folds, in this case 5, and the model is trained and validated 5 times, each time holding out a different fold for validation. This gives a more reliable estimate of performance for model selection and hyperparameter tuning, before a final evaluation on the untouched testing set. Both techniques are especially important when data is limited, which is common in medical settings. This slide presents a method for detection of suspicious skin lesions, which I developed with colleagues at MIT around 2021, published in Science Translational Medicine. This paper, titled Using Deep Learning for Dermatologist-Level Detection of Suspicious Pigmented Skin Lesions, from wide-field images to address a serious global health burden, particularly skin cancer. Around 96,480 people were diagnosed with melanoma in the United States in 2019, leading to 7,230 reported deaths, and early identification of suspicious pigmented lesions in primary care could enable dramatically less mortality and a possible 20-fold reduction in treatment cost. The system uses deep convolutional neural networks applied to 38,283 dermatological images from 133 patients and public sources, classified by 3 board-certified dermatologists. On the right, the pipeline is shown. A primary care visit produces a wide-field image. A multiscale blob detector finds candidate lesions. An intrapatient database is built. A pre-trained AsCNN extracts features, and fine-tuning classifies each region. The system achieved more than 90.3% sensitivity and 89.9% specificity in distinguishing suspicious lesions from non-suspicious lesions, skin, and complex backgrounds, and it extracts an intrapatient lesion saliency, an ugly duckling ranking that reached about 82.96% agreement with dermatologist rankings. This is a powerful example of computer vision enabling rapid, low-cost triage that could improve early melanoma detection in primary care. This slide continues the suspicious skin lesion example with an animation from Soengsen and colleagues in 2021. The animation begins with a wide-field photograph of a patient's back covered in many pigmented moles. It then overlays the system's detections, drawing boxes around individual lesions and color-coding them, with yellow and red boxes flagging the more suspicious ugly duckling lesions that stand out from the patient's typical mole pattern. Next, it shows a saliency heat map, where each lesion is highlighted by a soft-colored glow. Warm colors marking the lesions the model considers most atypical and therefore most worthy of clinical attention. The animation makes vivid how the system scans an entire region of skin at once, ranks lesions by suspiciousness, and directs the clinician's eye to the few lesions most likely to matter, which is exactly the ugly duckling reasoning dermatologists use. This slide presents detection in breast cancer screening from McKinney and colleagues in Nature in 2020. The paper, titled International Evaluation of an AI System for Breast Cancer Screening, shows ROC curves of sensitivity against 1- specificity for predicting breast cancer in the United States, both at 2 years and at 1 year. In both panels, the black AI curve lies above the purple MD readers curve, meaning the CNN-based system outperformed expert radiologists at detecting breast cancer from mammograms. On the right are 2 mammograms showing a breast cancer case that was missed by a radiologist but detected by the AI, with the lesion boxed in orange. This is a landmark study demonstrating that deep learning can match or exceed expert human performance in a high-stakes screening task, though of course such systems still require careful prospective validation before clinical deployment. This slide shows semantic segmentation for biomedical image analysis, with 2 examples. The top row, from Dong and colleagues at MIUA in 2017, shows brain MRI slices with original image, ground truth, and model segmentation for 2 cases, with tumor regions accurately overlaid in red and cyan. The bottom row, from Soleimani and colleagues on Arakshev in 2019, adds a crucial 4th panel: original, ground truth, segmentation, and uncertainty. The uncertainty map shows where the model is unsure about its prediction, which is essential in medicine, because the segmentation is far more trustworthy when it comes with a calibrated estimate of its own confidence. Flagging uncertain regions lets clinicians know where to look more carefully, rather than blindly trusting the output. This slide shows the breadth of biomedical segmentation, with the segment anything in medical images work, from Ma and colleagues in 2024. It displays a large montage of segmentation results across the entire body: brain tumors, retinal images, chest and lung CTs and X-rays, abdominal organs, spine, skin lesions, endoscopy, pathology, and more, all overlaid on a schematic human body. The point is that a single foundation model approach, MedSam, can be prompted to segment an enormous variety of structures across many imaging modalities and anatomical regions. This represents a shift toward general purpose, promptable segmentation models in medicine, rather than a separate bespoke network for every organ and modality. What we're looking at here is an architecture summary of Meta's Segment Anything model, which is the foundation of MedSam, broken into its 3 core components: the image encoder, the prompt encoder, and the mask decoder, starting with part 1, the image encoder. SAM begins with an input image of 3 channels at 1024 by 1024 resolution. This image is divided into non-overlapping patches of 16 by 16 pixels, yielding 64 by 64, or 4096 total patches. Each patch, when flattened, contains 768 values, 3 channels times 16 times 16. These patches are passed through a linear patch embedding layer, projecting them into a higher dimensional space, in this case, 1280 dimensions. The resulting sequence of 4096 tokens, each of dimension 1280, is then processed by a vision transformer. Positional embeddings are added to preserve spatial information, and the transformer encoder produces contextualized vectors of the same shape, 4096 by 1280. These context vectors are reshaped back into a spatial grid of 1280 channels at 64 by 64 resolution, and finally projected down through a channel projection to a fixed embedding size of 256 by 64 by 64. This is the image embedding that everything downstream will condition on, and critically, it only needs to be computed once per image. Moving to part 2, the prompt encoder. Notice that this component is deliberately lightweight. There is no self-attention and no transformer layers here. SAM accepts 3 prompt types: point prompts, given as coordinates with a foreground or background label, and bounding box prompts, given as corner coordinates, are both handled through coordinate normalization, positional encoding to 256 dimensions, and learned type embeddings, producing n-point embeddings and 2 m-box embeddings respectively, each of dimension 256. These sparse prompts are concatenated into a single set of n plus 2 m tokens. The third prompt type is a dense mask prompt at full input resolution. This is downsampled to 64 by 64 and passed through convolutions that project the single channel mask into 256 channels, matching the shape of the image embedding, so the 2 can simply be added element-wise. Before decoding, 4 learned output tokens are prepended to the sparse prompt embeddings, 3 mask tokens and 1 IOU token, giving a final token sequence of n plus 2 m plus 4 tokens of dimension 256. Finally, part 3, the mask decoder. This is where the prompt tokens and the image embedding interact. The decoder runs a 2-way attention block, repeated twice. First, self-attention among the tokens. Then token-to-image cross-attention, where the tokens attend to the image embedding, an MLP, and then image-to-token cross-attention in the reverse direction, allowing the image embedding to be updated by the prompts as well. The updated image embedding is then upscaled to higher resolution, while the mask tokens are passed through small MLPs. The final segmentation masks are produced by taking a per-mask dot product between each mask token and the upscaled image embedding, a spatially dense classification. In parallel, the IOU token passes through its own MLP head to predict a quality score for each mask, which is how SAM ranks its 3 candidate outputs and handles prompt ambiguity. The key architectural insight is this asymmetry, a heavy image encoder run once, paired with a lightweight prompt encoder and decoder that run in real time, which is what makes SAM interactive and promptable at scale. This slide moves to image, to text, and multimodal models, illustrated with OpenAI's CLIP. CLIP learns a shared embedding space for images and text, so it can match an image to the most likely textual description without task-specific training. In the example, a photograph of a dish is scored against 100 one-candidate food captions, and the model ranks a photo of guacamole first at 90.1% confidence, above ceviche, edamame, tuna tartare, and hummus. The small inset shows CLIP correctly labeling flower images as dandelion and daisy. This is a zero-shot classification. By embedding images and text into the same space, the model can classify against arbitrary label sets described in natural language, which is the foundation of modern multimodal and vision language systems. This slide is a montage titled Impact of Deep Learning for Computer Vision, showing the astonishing breadth of applications. We see autonomous driving, robotic manipulation, artistic style transfer applied to the Mona Lisa in the style of Van Gogh, object detection labeling people, a skateboard, and a dog, semantic segmentation of street scenes, facial landmark meshes, medical CT analysis, and a nature cover on AI-powered detection of skin cancer, titled Lesions Learned. The message is that the same underlying deep vision architectures now power an enormous range of real-world systems, from transportation and art to detection, biometrics, and medicine. This slide continues that montage with a grid focused entirely on biomedical imaging. It shows a rich collection of neuroimaging and medical visualizations, functional activation maps, cortical surface reconstructions, diffusion tractography of white matter fibers, cardiac MRI, tumor segmentations, brain parcellations, and registered anatomical atlases. The point is that deep learning for computer vision has become pervasive throughout biomedical research and clinical imaging, touching nearly every modality and organ system. This is the payoff of everything we have discussed: architectures that turn images into structured, learnable representations, now applied across the full landscape of medicine. This slide shows the broader course agenda, placing today's lecture in context. This slide lists the resources for this lecture, such as Chapter 6 and 7 of Deep Learning for Computer Vision by Shanmugamani and the foundational ViT paper. An image is worth 16 by 16 words. Transformers for Image Recognition at Scale by Dosovitsky and colleagues. Under software, the recommended tool is Google Colab at colab.research.google.com, which lets you experiment with pre-trained vision models and transformers without configuring a local GPU environment. I strongly encourage you to go beyond simply calling these models. Inspect the patch embeddings, the class token, the position embeddings, the attention maps, and the class predictions, so the architecture becomes concrete rather than abstract. To summarize today's journey, we saw how vision models evolved from hand-engineered features to end-to-end CNNs, and then to vision transformers that treat image patches as tokens, and use self-attention to model relationships across the whole image. We saw that ViTs match or exceed CNNs in accuracy and robustness, that hybrid and efficient designs make them deployable, and that these architectures now power detection, segmentation, and multimodal image-to-text systems across medicine and global health. The core idea to carry forward is that attention turns an image into a set of tokens, whose relationships are learned and dynamic, and that this flexible general representation is what makes modern computer vision so powerful for biomedical applications. Thank you, and see you next time.